Hello, my name is Ivan Borodi, and I would like to present our research on comparative analysis of large data processing in Apache Spark using Java, Python, and Scala programming languages. I would like to acknowledge my co-authors, Ilya Fedorovich and Halina Sukhivska, for their contributions to this work. Nowadays, processing large amounts of data is a key challenge, as data volumes are constantly growing. It's important to develop tools that provide efficient and reliable big data processing, analysis, and management. Apache Spark offers in-memory parallel execution on clusters and supports Java, Python, and Scala. This study implements a unified approach to testing ETL process components, extraction, transformation, and loading into Apache Iceberg tables. Since the impact of programming language on ETL performance is rarely studied, this comparison is highly relevant. Several researchers have studied the performance of Apache Spark for big data processing. They show that Apache Iceberg delivers excellent performance when reading large datasets and running analytical queries, outperforming formats like ORC, Parquet, Data Lake, and Apache Hudi. Compared to Hadoop MapReduce, Spark performs significantly faster, benefiting from in-memory processing for both batch and streaming workloads. Components such as Spark SQL demonstrate Spark's flexibility and efficiency. In this study, there were chosen two data sources for processing by Apache Spark. The first dataset contains fields such as city, country, latitude, longitude, etc. The file size is about 5 megabytes. The second dataset provides hourly temperature records for the year 2024. It includes timestamps, temperature values in degrees Celsius, and matching geographic coordinates. The file size is approximately 1.6 gigabytes. Here is the ETL workflow and tools used in our analysis. We extract data by reading CSV files into Spark data frames, transforming them by joining datasets, applying partitions, and cleaning. Then the results data are loading into Apache Iceberg tables. The analysis includes three stages: loading city data into World Cities table, loading temperature data into Weather Events table, and uploading unified data into Weather Hourly Events table. Development was done in PyCharm for Python and IntelliJ IDEA for Scala and Java. Here you can see which Spark configurations we set up for running ETL processes. On the computer used for the experiment, the JVM heap size was approximately 4 gigabytes, with up to 12 parallel tasks running on 12 cores. We used Spark in local mode with multi-threading to run Spark task in concurrency mode. For working with Apache Iceberg tables, we defined a specific catalog and enabled Spark extensions to support Iceberg features. In terms of resource allocation, we configured 5 executors, each with 2 CPU cores. The driver, which coordinates the processing, was assigned 2 CPU cores. The experiment was running on the same computer, which has the following software hardware parameters. Operational system is Windows 10 Home, 64-bit. RAM memory capacity is 16 gigabytes, and processor AMD Ryzen with Radeon graphics 3 GHz. Here you can see the experiment results measured in seconds, showing Apache Spark ETL performance across Java, Scala, and Python. For the lightweight World Cities table, Python has the fastest execution. In processing the larger Weather Events table, over 1.6 gigabytes, execution times were similar. Loading the more intensive Weather Hourly Events table, Scala performed fastest, followed by Java, while Python was significantly slower on this task. The study shows that Spark ETL performance varies with the programming language used, even under identical configurations. Python outperforms Scala and Java for small volume ETL due to lower initialization overhead and optimized data frame operations. For large-scale partitioned writes, Scala delivers up to 1.6% faster execution than Java and 6% faster than Python, making it well suited for partitioned Iceberg pipelines. Additionally, Iceberg's partitioning and versioning features further improve ETL efficiency and optimize storage. Regarding further research, building on the findings of the study, several directions for further research are proposed. Development of reliable and optimized systems that will load data into Iceberg tables on a regular basis. Then explore lakehouse storages like Data Lake and Apache Hudi, and benchmark performance in cloud native deployments. Thank you for your attention.